The grid just went down. It's been raining for 3 days straight. Your solar panels are producing nothing. The clouds aren't breaking. The sun isn't coming. And your $20,000 solar setup is sitting there completely useless. Most preppers think solar is the answer. They stockpile panels, inverters, and lithium battery banks. They spend $20,000 building the perfect off-grid power system, and they feel completely safe doing it. But there's a physics problem nobody talks about. Moving water doesn't care about clouds. It doesn't care about winter. It doesn't care about the grid going down. A creek running 50 FT from your cabin is generating kinetic energy right now, 24/7, completely free. Today, we're breaking down the physics of micro-hydropower. We're covering flow rate, hydraulic head, and Bernoulli's principle. And we're going to show you exactly why a $50 water wheel outlasts every solar setup ever built. Here's the proof that this isn't a fringe idea. Micro-hydropower currently provides electricity to over 1 billion people worldwide. It's not new. It's not experimental. It's physics that's been working for centuries. Solar panels are the most popular survival power solution on the market. Walk into any prepper forum, and 90% of power recommendations point to solar. But solar has a fundamental physics weakness that nobody in the sales brochure mentions. Solar panels need direct photons hitting photovoltaic cells to generate electricity. No photons, no power. And the conditions that cause grid failures are exactly the conditions that block photons. Storms, heavy cloud cover, winter, smoke from wildfires. These aren't edge cases. These are the crisis scenarios you're actually preparing for. A fully overcast sky reduces solar output by 70 to 90%. A light cloud cover cuts it by 50%. And in winter at northern latitudes, you're getting maybe 6 hours of weak sunlight on a good day. 6 hours of reduced output in a 24-hour emergency. Generators seem like the obvious backup, but generators need fuel. Fuel runs out within 72 hours during a regional crisis. Every prepper in your area is buying the same fuel at the same time. Fuel gets stolen. Fuel makes noise that broadcasts your location to anyone within a quarter mile. A running generator is an invitation. Lithium battery banks store energy, but they don't generate it. And here's what the spec sheets don't mention. Lithium batteries lose up to 20% of their capacity when temperatures drop below freezing. The exact moment a winter storm knocks out the grid is the exact moment your battery bank is running at 80% of its rated capacity. The average prepper spends $20,000 on a system that underperforms in clouds, fails in winter, and runs dry in 72 hours. The failure isn't bad luck. It's physics. And the solution is a completely different physics principle that's been sitting in the creek behind your cabin this whole time. Water moving downhill is carrying kinetic energy. It doesn't stop at night. It doesn't stop in a storm. In fact, storms make it stronger. It doesn't shut down in winter unless it freezes completely solid. And even a modest trickle of moving water carries more harvestable energy than most preppers ever realize. The physics starts with flow rate. Flow rate measures how much water moves past a given point per second, expressed in cubic feet per second. Even a small mountain stream running at 1 cubic foot per second is moving 62 pounds of water every single second. 62 pounds of mass carrying kinetic energy continuously into your turbine blades around the clock. But flow rate alone doesn't tell the whole story. The second variable is hydraulic head. Hydraulic head is the vertical height difference between where water enters your system and where it exits. And this is where the physics gets really powerful. Every foot of vertical drop multiplies the pressure and velocity of water hitting your turbine. A stream dropping 10 feet through a narrow pipe generates dramatically more power than the same stream flowing flat across a wide open channel. Height converts directly into speed. Speed converts directly into electricity. That relationship is non-negotiable physics. This is where Bernoulli's principle enters. Bernoulli's principle states that as fluid velocity increases, pressure decreases. When you force water through a narrow nozzle, it accelerates. That acceleration is exactly what drives a turbine efficiently. A 2-in nozzle fed by a 10 phi head of water generates enough continuous output for cabin lighting indefinitely. Not occasionally, indefinitely. Here's the number that puts it in context. The kinetic energy of flowing water scales with the square of its velocity. Double the velocity, and you don't double the energy, you quadruple it. Every design choice that increases water velocity through your system pays back 4 times over in electrical output. That's the physics advantage solar can never match. Sunlight intensity doesn't square. Water velocity does. The physics of microhydro is fundamentally different from solar. Solar harvests energy that arrives intermittently and stores what it can catch. Microhydro harvests energy from a continuous physical process that never stops running. And that difference is everything when the grid goes down in the middle of a 3-day rainstorm. You don't need expensive equipment to harvest moving water. The core components of a functional microhydro system cost $50 if you source them correctly. Here's what you need. A salvaged car alternator from any junkyard, typically $5 to $15. PVC pipe in 2 in diameter for the nozzle and intake, roughly $10 to $15 for the length you need. Plastic paddle blades cut from food-grade containers or heavy-duty plastic sheeting. Basic hardware including a shaft, bearings, and wire to connect the alternator output to a charge controller. The alternator is the key component. Car alternators are engineered to convert rotational mechanical energy into electricity under continuous load. They're designed to survive vibration, moisture, and temperature extremes for the lifetime of a vehicle. A salvaged alternator is pre-built for exactly the operating conditions a creek motor runs in. Now, here's the physics of why blade geometry matters more than blade size. A flat blade striking water head-on deflects the water, but captures only a fraction of the available kinetic energy. The water hits and bounces. Energy is wasted in turbulence. A curved blade channels water across its surface and captures momentum through the full arc of rotation. It doesn't just stop the water. It redirects it, extracting energy continuously through the whole stroke. The curvature angle determines efficiency. Bigger flat blades don't outperform smaller curved ones. The physics won't allow it. The nozzle diameter versus flow rate trade-off works like this. A wider nozzle moves more volume, but at lower velocity. A narrower nozzle moves less volume, but at higher velocity. Remember the velocity-squared relationship. For a low-head system with minimal vertical drop, a wider nozzle captures more energy from raw volume. For a high-head system with significant vertical drop, a narrow nozzle concentrates velocity and maximizes the kinetic strike on each turbine blade. Match your nozzle diameter to your creek's actual head measurement, not a generic diagram, your specific creek. The 3 most common build mistakes all come from ignoring the physics. First mistake, placing the turbine in flat, slow water. Flat water has low kinetic energy. You need velocity, which means you need either a vertical drop or a narrowing channel that forces acceleration. A beautiful, wide, calm creek is almost useless. A narrow, rocky chute is a power plant. Second mistake, building blades too large. Oversized blades create rotational resistance. That resistance slows the alternator below its minimum efficient operating speed. A car alternator needs to spin fast to generate useful voltage. Big, slow blades fight that requirement directly. Third mistake, skipping the charge controller. Raw alternator output fluctuates with water speed. Rain increases flow. Debris temporarily blocks the intake. Voltage swings constantly. A basic charge controller costs $10 and protects your battery bank from voltage spikes that would destroy it within 48 hours. $10 protects your entire investment. The build is simple. The physics behind it isn't. And the gap between a working system and a pile of wet junk usually comes down to which of those three mistakes you made. Municipal stormwater systems are engineered with hydraulic head built directly into their design. Civil engineers calculate pressure differentials, pipe diameters, and flow velocities to move millions of gallons of water efficiently across elevation changes every single day. Every city is full of moving water systems carrying exactly the physics microhydro needs. Stormwater mains drop elevation intentionally. That's how gravity-fed drainage works. Water flowing through a municipal drainage pipe is often moving faster than a natural creek because pipe geometry concentrates it. A rough creek bed creates friction that slows water down. A smooth PVC municipal pipe removes that friction almost entirely. Same volume of water, higher velocity, more kinetic energy at the turbine. Pipe diameter controls velocity the same way a nozzle does. A 12-in main flowing at capacity carries enormous kinetic energy through its cross-section. The pressure differentials designed into urban drainage infrastructure don't disappear when the power goes out. They're gravity-fed. They operate on physics, not electricity. In a grid-down urban scenario, stormwater systems keep functioning. Rain keeps falling. The engineered elevation changes keep driving flow. And the physics principle is identical to a rural creek motor. Hydraulic head, flow rate, nozzle velocity. The source is different. The physics is the same. This matters because most urban preppers dismiss microhydro entirely. They assume it requires wilderness. It doesn't. It requires moving water with elevation change. Cities have that by engineering. The infrastructure your city built to manage flooding is simultaneously a continuous power source, sitting completely untapped, running on physics that doesn't care whether the grid is up or down. Capacity factor is the metric that finally exposes solar's real performance gap. Capacity factor measures what percentage of a system's maximum rated output it actually delivers average across a full year. Not peak output on a clear July afternoon. Average output across every night, every storm, and every gray winter week. Solar panels in the United States average a capacity factor of 15 to 25%. That means a 10-kilowatt solar system actually delivers the energy equivalent of 1.12 to 2.1 kilowatts when you average it across the full year. Nights drag it to zero. Overcast days cut it by half. Winter compresses the generation window to a few weak hours. The rated number on the box is a best-case marketing figure. Micro-hydro systems running on a consistent stream operate at a capacity factor of 40 to 60%. A stream that flows year-round delivers power through every night, every storm, and every overcast winter week. The physics doesn't pause for darkness. It doesn't pause for clouds. It pauses for one thing: ice, and only complete freezing stops it entirely. Now run the 10-year cost comparison honestly. A $20,000 solar setup at 20% capacity factor delivers roughly 4,000 kilowatt-hours of usable energy per year on average. Solar panel degradation reduces that output by about 0.5% annually. Inverters need replacement every 10 years, adding another $2,000 to $3,000. Battery banks degrade faster than panels. The true 10-year cost of a solar system is well above $20,000. A $50 micro-hydro build on a consistent stream at 50% capacity factor on a modest output system delivers comparable annual energy. Maintenance means clearing debris from the intake screen occasionally and greasing a bearing once a year. No inverter replacement, no battery degradation cycles, no panel cleaning schedule. The weather independence factor is the one that should permanently change how every prepper thinks about power. The exact meteorological conditions that trigger a grid failure, heavy storms, extended cloud cover, winter weather events, are the exact conditions that increase water flow in creeks and stormwater systems. The worse the weather gets, the more water is moving. The more water is moving, the better your micro-hydro system performs. Solar and hydro aren't just different power sources. They have opposite relationships to crisis conditions. One fails when things get bad, the other gets stronger. That's not a preference, that's physics. The most expensive survival mistake isn't buying the wrong gear, it's trusting gear that fails exactly when you need it most. You now know why moving water beats a $20,000 solar setup in every scenario that actually counts. But power is only half of the survival equation. The other half is water you can actually drink. And here's something most preppers never considered. Finding water is the easy part. The creek that just powered your cabin might be silently poisoning you at the same time. There's a phenomenon called the clear water fallacy, and it kills more people in survival scenarios than dehydration does. If this breakdown of physics has changed the way you view the energy flowing through the landscape, please subscribe and like the channel. We are uncovering the survival truths that the mainstream tries to bury. Power your future. Our next deep dive into the hidden resources of the world will be opening soon.